Alright, so we were discussing CSPs, okay, and we were almost towards the end of it, so maybe I'll just scroll it. Right, so we had talked about all these things. Cut set conditioning was done as well, and alright, so now we come to iterative improvement. Okay, so we start with iterative improvement now, and we'll do it for n-queens problem. Local, अब चुप हो जाओ भाई. Local search methods typically work with complete states. That is, all variables assigned. So red, you can't put both red in the examples we have seen. To apply to CSPs, take an assignment with unsatisfied constraints. Operators reassign variable values. No fringe, live on the edge. We'll see what does it mean. So what we are doing here, take an assignment with unsatisfied constraints. If constraints are satisfied, in that case, see, what is the problem to begin with? You have to solve a problem for all the variables. Variables will take values from their domains, and what has to be satisfied? The constraints. Okay. So it says take an assignment with unsatisfied constraints. Why would one do that? Why this statement? So if you have an assignment that already satisfies the constraint, then there is nothing to do with. Okay. So you have to assume the other way around, that you take an assignment with unsatisfied constraints. Operators reassign variable values. No fringe, live on the edge. So in this case, for example, this was the graph problem. Is this a valid assignment? No. So what you do is you change this to blue, and this is fine now. Okay. So this is the algorithm. While not solved, variable selection, randomly select any conflicted variable. Value selection, min conflicts heuristic. Choose a value that violates the fewest constraints. For example, hill climb with hn, total number of violated constraints. So this algorithm is very simple. What are you doing? While not solved. What does it mean, while not solved? While constraints are not satisfied, choose a variable randomly and randomly select any conflicted variable. In this case, both were conflicting, you could choose any of the two. Choose a value that violates the fewest constraints. Right? So if you have 4 constraints violated, then choose a value that violates the fewest constraint. We'll see what does it exactly mean. Hill climb with hn, total number of violated constraints. This is a perfect example to show everything that we have been doing. I mean, for this algorithm. What is h equal to 5 here? Can you guess? What is h equal to 5? Total number of attacks, right? So this is a 4 cross 4 grid, 4 cross 4 chess, 4 queens are there, and you are having position is such that there are 5 possible ways of attack in this. So you put this h equal to 5. Now what has happened in this case? Which one goes where? So this one goes up. What is the value of h now? 2. Further, these two guys still remain the same. This comes down, h equal to 0. So what is this algorithm essentially doing? How do you start? See, in contrast with everything else that we have done until now. अभी तक हम क्या कर रहे थे? There used to be a start node called root node. Okay? And उसकी क्या property थी? No values assigned, nothing. It was empty. Then you were, for each level, you were assigning a value to a variable from their domain. What was the last level? Last level was the level of where everybody was assigned some value, but they all may or may not satisfy the constraint. So we were looking for the states where constraints are satisfied. Okay? In this case, what is your start state? Where are you starting from? Is this the state of maximum attacks? See, this can't be maximum attacks. Why? But anyway, I won't go into that. Because these two are still not attacking each other. So can you have a state? But that's the material for our question right now. So in this case, how are you starting? You randomly assign all variables some value. Right? So you you are not starting where you have not assigned anyone anything. How would you solve this problem if you were going that, that tree way? Board will be empty initially. Then you put one queen. Then you put second queen, making sure that it is not attacking first one. Then you put third one, making sure that it is not attacking. And so there are no attacks. And you keep on iteratively doing it. Here you are saying start with whatever. Okay? Number of constraints violated in this case are 5. Just try to reduce it. Now, let's go back to the algorithm. That will make more sense now. Randomly select any conflicted variable. Choose a value that violates the fewest constraints. Okay, hill climbing, we'll see it for a while. So this is what you are doing. I mean, if you understand this example, you understand what is going on in this iterative. What was the name of the algorithm? Iterative improvement. Thank you. Okay. All right, let's talk about these things now. States 4 queens in 4 columns. What is this number? Okay. What are operators? Move queens in a column. Goal test is no attacks. Evaluation is the number of attacks. So you start with a particular number of attacks and your goal is to keep on decreasing them until you reach 0. But I still don't understand this. Why are we talking about 4 columns? Can you just replace it with rows? No, that's okay, but can you just replace it with rows? Is it symmetric with respect to rows as well? Yes. Okay. So, what are the conditions required? We all know that if there has to be no attack, they all have to be in either different columns and different rows, right? So, that is how you start with. 4 queens in 4 columns. Why 4 into 4 into 4 into 4? So first queen can take values in 4 ways. Second queen can take value in, so 4.4.4.4. Okay. These many possible states are there. These many possible states you could have started with. And do we care which one? For this algorithm we don't. Okay. Does this solve this NP hard problem? Once NP hard, this is something that you have to remember. I think this is fine. So thank you. Okay.
Here we have 5 queens. And what I'm going to do is I'm going to run min conflicts for you. So what does it say? Well, first of all, this is not a particularly typical assignment, right? And you might think, okay, that's great. We started with everything in some reasonable position. In fact,
so in this case, they are starting row wise or column wise? Row wise. Okay, they are just symmetric.
this is about as bad as it's going to get for this problem, to start everything off altogether. This is very conflict. Okay, so what I'm going to do is I'm going to run min conflict. So I pick some variable which is conflicted. And my random number generator says row 2. Okay, so now what I do is I move this assignment.
What are these 2, 1, 1, 0? No, so what are these 2, 1, 1, 0? Just this. Right now it is 4. Right now it is 4 for all of them. So this guy can be attacked by 4 queens. The moment you move it here only 2. You move here only 1. You move here only 1, and there it is 0.
From the first column to a minimum column, which in this case might be here. Alright, now I pick another conflicted variable, and my random number generator says row 4. Now I've got multiple choices, so I'll pick one. Let's say.
What do we do next? What do we do next? So let's say let them choose which one? This one. So shall I go here or any of these guys? Any of these guys, okay?
Now I've got multiple choices, so I'll pick one. Let's say this one. I pick a conflicted variable. Does not have to be the most conflicted variable. Maybe this one. I move it somewhere. And then I continue this process. Maybe I pick this one. I move it here. Maybe I pick this one. And I move it here. And now I'm done. Okay. So instead of building things up step by step, we start with a complete assignment and we try to fix problems.
Okay. So what was done in this algorithm? Start with a complete assignment and keep on removing the conflicts until you are done. What is the worst case complexity of this algorithm? Huh? It is still exponential. Okay? Alright, so
let's now look at iterative improvement on this graph. So what do we
so let's first understand, okay, iterative improvement.
See right here? We see a complete assignment, everything's been colored, but there's all kinds of violations of the map coloring constraint. So in orange, we see all the violations. So when I click next, what's going to happen is some conflicted variable is going to have its value reassigned. Right? So it was that one. Then we do it again, and again, and again, and again. And we keep doing this step by step. And now we're done. So it can be very effective in practice.
Okay. So now coming to the performance of this algorithm. Right, so see this huge gain. Given a random initial state, one can solve n queens in almost constant time for an arbitrary n with high probability. With high probability, so you are not guaranteed. For n equal to even 10 million. Remember what was this number for previous algorithms? देखो, DFS with backtracking, we said it was n equal to 25 के आसपास. Then MRV, LCV, R consistency and all those, that made it possible for n equal to 1000, right? And now if you see 10 million, and that too in almost constant time. So this is a powerful algorithm, but does it solve it? No. The same appears to be true for any randomly generated CSP, except in a narrow range of ratio where the number of constraints divided by the number of variables takes some value r. Okay. So CPU time, that means time complexity, for every other value is fine, but there exists some ratio for which the problem still becomes, so you can't solve it in a time lesser than exponential. And as long as such a thing exists, you can't say that the problem is tractable. Okay, it's still NP hard. So there are still hard versions of the problem, and once you are here, you are done. So CSPs are a special kind of search problems. States are partial assignments. Goal test is defined by the constraints. Basic solution is backtracking search, and then we talked about these kind of speed ups, and finally we talked about iterative min conflict is often effective in practice. So this is what you often effectively use in practice. Local search. How many of you know? All right. So, how many of you know about gradient descent? How does it work? So, hill climbing is roughly opposite of that in discrete version, not in continuous. Gradient descent works in a continuous space. So, tree search keeps unexplored alternatives on the fringe. Local search improves a single option until you can't make it better. What was this? Which algorithm? Iterative algorithms. New successor function, local changes. So generally much faster and more memory efficient, but incomplete and suboptimal. But since problems are NP hard, so you do all your best that you can do. So this can actually give rise to any of these situations, which is just fine. So hill climbing is simple general idea. Start wherever, repeat, move to the best neighboring state. If no neighbors better than the current, quit. What's bad about this approach? Is it complete? Why no? Huh? Right. It may find a local minimum and local maximum and stop there. Optimal? No. Okay. What's good about it?
It gives some sort of solution.
Right. So it's a good heuristic. Might eventually take you there if things are fine, and is computationally less expensive. So this is a good quiz. If you start from here, so tell me, if you start from here, where will you reach? Using hill climbing? Here or here? So if you start from here, you will reach here. If you start from here, right? You see no other value better than the current one, so you don't have an incentive to move. But if you start from here, then you will reach here. If you start from here, shoulder, and so on. So you guys know it. Yes. 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 Starting from X. So starting from X, where will we reach? Starting from X, we will reach to B. Fine. Starting from Y, right? So it takes us here. Starting from Z, Z is where? Z. From Z you go to E. So this is all fine. Simulated annealing. Genetic algorithm. So I'll just skip because they are just one slide thing. Not because they are actually one slide, there are different. So, कौन सा? कौन सा? हाँ. But that is fine. Whatever works for discrete will work for most likely continuous too. बस इसमें क्या था देखो problem. Okay. So let me just take up that thing again. So how are you talking about hill climbing in this case? So where is hill climbing in this case? What does hill climbing mean? You are at a state, you have particular numbers, whichever number you want to maximize, optimize. If all your states to which you can reach from this state, they give you a value better than this one, you go to that state. else you just stay wherever you are, as simple as this. Okay. So in this case it works even if it is a discrete state space, it doesn't have to be continuous. What is with gradient descent? Because it works on those discrete values. In this case it will work on the number of attacks, the h that you have designed. In case of gradient descent, what happens? In case of gradient descent, you depend on gradient, and for that you require that function to be not just continuous but also differentiable. Okay. All right, so we are done with these slides now. So only until here we don't have the rest of the things in our course. All right, so we come to adversarial search now. All right, so we start with it now. What do you understand from this slide? What are we going to discuss? So now we are talking about, so until now we were talking about just one player game. There was only one player. Now we are going to talk about two player games. So we are going to talk about adversarial search now. What is adversary? Adversary is basically opponent. So games that will fall in here are, for example, tic-tac-toe, chess, okay, where you have a, so where when you lose your opponent wins, and when your opponent loses you win, okay. Okay, so checkers first, I mean this is history, we just skip this. Behavior from computation, Pac-Man, and now we will bring the ghosts in. Until now we didn't really talk about that much. Again I have to do it. Okay.
So I'll run this in a second, and what I want you to think while I run this is what kinds of computations must be happening inside this Pac-Man playing agent in order to give rise to the variety of behaviors that you see.
Okay. Next. So in this case, Pac-Man had adversaries that it had to take care of. Adversarial games. There is one contention for which both the players are working for. So types of games, there are many different kinds of games. Axis, deterministic or stochastic. Example of stochastic game? Stochastic and deterministic both. Is chess deterministic? Is chess deterministic or stochastic? So then give me an example of stochastic. Ludo. Okay. So Ludo, your turn depends on a chance. Okay. So Ludo might be stochastic. 1, 2 or more players. One player thing can be examples of one player game. Pac-Man. What else? Candy Crush. 2. Chess. Tic-tac-toe. More players. Ludo and so on. Zero sum. What is zero sum? This is an important concept. You can talk about game theory, you can talk about economics, this thing comes everywhere. Perfect information. Can you see the state? Okay. So depending on these things, we'll talk about our games. We want algorithms for calculating a strategy, a policy. We have already started talking about reinforcement learning kind of terminologies here. So we want algorithms for calculating a strategy which recommends a move from each state. So ये सब बताओ एक बार. What are we going to talk about? Given a state, tell me what should my next state be, right? But does it depend completely on me in case of two-player game? No, it depends on my adversary too. Deterministic games. Many possible formalizations. One is there is a state S, you start at S naught. Players 1 to N usually take turns. Actions A may depend on player and state. Transition function. What does this mean? S cross A to S. So what does it mean to say function? Transition function S cross A to S. Right. So you are in a state, you take an action and that takes you to the another state. Terminal test is S belongs to T or F. Terminal utilities. What is this now? So start, in a state, player does something and then you get a R. So solution for a player is a policy S to A. What is S to A? Given a state, give me the action that I should take in this particular state. We'll come to this. R is a real number. Utilities are real numbers. Okay. Everybody more or less gets these things? Simple, fair enough. Zero sum. Okay. Right. Zero sum is agents have opposite utilities, values on outcomes. Let us think of a single value that one maximizes and the other minimizes. Adversarial and pure competition. In this, agents have independent utilities. Cooperation, indifference, competition, more, all are possible. More later on non-zero sum game. So, what is a zero sum game and what is the other kind of games? Examples? Examples of zero sum? Examples of zero sum. Examples of zero sum? Chess. Okay? Tic-tac-toe. What about this here? Right? Where you don't have this strictly kind of adversary. Huh? So more complex games will fall in here. जिसमें? In this case? देखो, this is important here. Let us think of a single value that one maximizes and the other minimizes. So let's say if you are white in chess, you are going to attain +1. If I am black in chess, I want to attain exact opposite, which is -1. Attendance? चला दो यार, अभी तक ERP पे नहीं आई ये चीजें, यहाँ होने लग गई ERP पे। आज का कहा था कि आज के बाद से आ जाएगी। हो गई? ओके। हाँ, इसमें हाँ, इसमें तो बहुत सारे गेम्स आ जाएंगे, राइट? So, for example, anywhere where you can have 3 independent players, वो तो इधर आ ही जाएंगे। भाई 3 players में not, of course, it does not mean कि all 3 will fall in here, okay? But more than here, they will go here. So, for example, 3 people playing Age of Empires, right? If both of them attack the third player at once, then this becomes a cooperation. Zero sum कैसे हो गया दोस्त?
मतलब अगर मेरा हेल्थ बार में मुझे मैक्सिमाइज करना है मेरा और 2 प्लेयर्स को मेरा हेल्थ बार मिनिमाइज करना है, तो जीरो सम में आ रहा है ना?
सबको मैक्सिमाइज करना है, सबको मिनिमाइज करना है। सबको अपना हेल्थ बार मैक्सिमाइज करना है, दूसरे का मिनिमाइज करना है। नो No, see, zero sum, we'll talk about these things, more examples later. Problem is you are fighting for that same objective function. This is important here, that same objective function, right? When you want to win, you are of course trying to maximize something, you are trying to minimize things for the others. But in zero sum game, you have that same objective function that one is trying to maximize and you are trying to minimize. That same objective function, this is important. Okay? Adversarial search? Right. That objective function can be So you say there are three objective functions. Now what?
जैसे फाइटिंग गेम
हाँ.
ये बंदे की हेल्थ बार है बी बंदे की तो ये वाला चाह रहा है कि मैं मेरी हेल्थ बार मैक्सिमाइज करूं ये बेटर नहीं है तो उसमें दो हेल्थ बार है उसके पर्सपेक्टिव से सेम
नहीं. If your objective function is of this kind that I care about only my health, then I care about just this, not about the others. In this case, if opponent is doing better, then in some sense I am certainly doing exactly opposite on those terms. So let's say if I take a knight of opponent and opponent takes my knight, we are in some, let's say not counting the board positions, right, we are almost at the same state. Those kind of things. See, these are constructs that are there to understand things better. Does not mean that, they are completely foolproof. So for example, one knight gone from this side, one knight gone from that side does not mean that chess position is equal for both. Right? But somehow कैसे तो formalize करोगे ना चीजों को. अब आप board position को कैसे formalize करोगे? That becomes too much. You have 64 positions and if you start formalizing that too, you can, right? But in that case things become much more problematic. So again, like in all computer science, it's a question of what you lose versus what you gain. So if I keep track of everything including positions, right, I have to keep track of too much. That increases my complexity too much. So I don't want to go there, but whatever extent I can, I'll try to do that. What is there in this picture? So let's say we are blue.
Thinking ahead.
We are thinking that what? Adversary. So think of chess. I am thinking if I do something, what my opponent will do. But I don't have to stop at just one level. Inside this, keep on doing this, right? Now in chess, and I think everybody has played chess, okay? So if you play it with GNU chess, if you are doing look ahead, if you are doing look ahead for 4 states, that's considered easy, right? If you are doing look ahead till 8th state, that's considered as moderate, and 12 is hard, and 13, 14 is grandmaster's level. So if your computer reaches beyond 13, 14, 15, it crosses that grandmaster level as well. Okay? Single agent trees. So this we have been doing. So single agent trees, what is happening in here? Numbers को छोड़ो एक बार. You start from the start state. अभी पुरानी वाली चीजों पे जाओ. You start from the start state. Goal is to eat this guy. From here you have two options. You can go left. You can go right. So this one go left. This one go right. Now if you go left, you have again two options. You can go left and you can go right. So keep on doing this. We'll make a tree. We'll assign all these values. Okay. Now see these numbers in whichever way they are computing. Why is this best here and for everyone else it is lesser than 8? Because this was the shortest path to reach to this and you have reached here, right? So you are maximizing your utility. If you go in that direction, you will still be able to eat this, but utilities will be lesser. So these numbers will be lesser. That's what I am saying. Don't talk about the absolute values of these numbers. They are utilities. If I go and eat this pellet in this path, my score is 8. Okay? Any other path that I take won't help me get 8. Okay. Right, now we'll be talking about those T and F as well. So, you start from here, that same diagram that we had seen in the previous slide. The value of a state is the best achievable outcome or utility from that state. So, if you see from that state, the best achievable outcome is this one. Of course, you will get this one through other things too, but that will not be the best achievable way for this one. These are the terminal states. What are the terminal states? Where your game stops. Okay. Non-terminal states. What is this guy? Attendance sheet कहाँ तक है? I think we'll take a 10 minutes break and then come back.